Alright, excuse me, factorising polynomials. So, just like we've been doing in methods, I'm going to use the remainder and factor theorems. To help us out. So, let's have a look at some examples. So the first one, we're going to factorise. Polynomial z equals z cubed plus z squared plus 4. And so we would do the same kind of stuff here as what we did in methods. So we make some choices. So what number would you like to try? Any particular numbers?
2.
The number 2?
No.
Not 2?
Negative 2.
Negative 2? Yeah, 2's not a very good number, isn't it? Just like you can, sometimes you can get a bit of an idea. Because if you use 2, that's positive, 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 and you add them together, so you're going to quite clearly get something that's bigger than 0. So you're going to need some negatives in there somewhere. So negative 2 is probably a good choice. And again, you can kind of look and you can have, oh, well, if I choose negative 1, well, that's probably not going to give me enough because that'll be negative 1, positive 1. So sometimes you can get a bit of an idea as to what you might try. And so we've got negative 8 plus 4 plus 4, which is 0. So from that we know that z plus 2 is a factor. Alright, and so then you need to divide that in, see what you get. And so we've got z cubed plus z squared plus no lots of z plus 4. We're going to do the long division to try synthetic if you wanted to. But you've got to be a little bit careful with synthetic because sometimes common factors in there can throw the synthetic out. Alright, so what do we got here? To get z cubed, we've got times it by z squared. So we've got z squared plus 2z squared. Then we're taking that away. Oops, z cubed to there, sorry. First one. So minus z squared plus 0 lots of z plus 4. So minus z. Minus z squared minus 2z, got to take all that away. So it's 2z plus 4. And then plus 2 on the end. And then we're taking that away and we get 0 as we knew. Alright, so now we've got our polynomial factorised to z plus 2. Then z squared minus z plus 2. Now if we're in methods we would stop there because in methods we work with the real numbers, but we've got complex numbers available to us, so we need to factorise this one. And so to do that we need to use the complete the square. Alright, so I'm just going to work with the z squared minus z plus 2 part, and then come back. So next line down is
Z minus a half.
minus a half. So then we would have, then we expanded plus a quarter up here, so we're going to take a quarter there. And we take a quarter from 2, so that's 8 quarters minus 1 quarter. So 7 quarters. Now also here we've got a plus, so we need to
I squared.
I squared, we need to bring in, yep. Change that to a negative. 7 on 4 I squared. Whoops, forgot my square there. So now I can treat this as a difference of perfect squares. And so this next line down then, z minus a half in the front of each bracket, plus in one bracket, minus in the other, square root of 7 over 2, and I. So, our polynomial, when we factorised it, then is z plus 2, z minus a half plus root 7 over 2i, and z minus a half plus root 7 over 2i. Alright, anything in that I went too fast for you? Alright, let's look at another example. Alright. This one here, so we've got some complex in the coefficients and things here. But does anybody notice anything about those 4 terms? Nothing in particular? What about the last 2 terms you've got there? You've got a 4 in it?
4.
And these two have got some z's in them. So another method, and you often overlook this method, is to group. So if I group the first 2 terms together and the last 2 terms together, then have a look and say, well, in the first 2 terms, z squared is a factor, and so then we've got z minus I. Now, when we are grouping things, what we're aiming to do is get this bracket part to be the same so we can take it out as a common factor. So when you look at here, you've got the 4, but if I just take 4 out, I'm going to have minus z plus I, which is not exactly the same as they're different. So if I take negative out as well as 4, then I'll have z minus I, and I've got these 2 brackets that are the same, which is a common factor which we can take out. Then the other bracket is z squared minus 4, and what do you notice about that bracket? Difference of perfect squares, yep. So we've got z minus I, z plus 2, z minus 2. Now you could, of course, have used the remainder of factor theorem. Z2 would work, so z minus 2. All right. Now, there is a theorem. It's all we've done when we've looked here. So far, we've just looked at normal numbers, but there is a thing called the conjugate root theorem, which we can use to help Alright, now the word conjugate that's in there, it's not just random use of the word. Alright, it refers to the conjugates. Alright, so if you have a polynomial, PZ is a polynomial with, and this bit's important, real coefficients. Alright, so over here in this previous example that we just did, you notice the z squared's got negative I, so that's not a real coefficient, it's got the I in it. So this conjugate root theorem doesn't apply to this polynomial, only to polynomials which have real coefficients. So what it says then is if a plus bi is a solution to pz equals 0, then a minus bi, which is the conjugate, so the root part is the solution, the conjugate is this one, and the theorem says that the conjugate is also a solution. Alright. Which makes sense when you think about it, because if you've got real coefficients but you've got a complex root, when you multiply complex by its conjugate, you get a real number. Alright, so you've got a complex factor, but you've only got real coefficients. Now you can turn that into a real number, or you do it with the conjugate. Alright, so let's have a look at an example.
When it says linear factors, does that mean real factors as
Well,
well?
not necessarily real,
Yeah. Just other factors.
other factors. So, here this is a linear factor
Yeah.
because it's said to the 1. So linear just means that your variable,
Oh, yeah.
in which case is z,
Okay.
is power of 1,
Yeah.
not z squared or
Okay.
whatever.
Yeah.
All right, so the first one says show that that is a factor. So we've got to show that z minus 1 plus root I is a factor. So what I'm going to do is I'm going to say, well, that's the same as, I put in brackets, oops, written that wrong, root 2i, not root I. If I take the negative out, root 2i. Alright, so I've got to show that that's a linear factor. So effectively what it's asking us to do calculate the polynomial when you put 1 minus root 2i in. Because if it is a factor, when we put this in, what should we get? We should get 0, because this is just what I'm doing here. It's really just the remainder theorem, isn't it? So we're told to show that that's a factor. So if I put the 1 minus root 2i bit in there, I should get 0 as an answer. So that is, if I be able to squeeze it in there, or I might be able to squeeze it. So I'm putting 1 minus root 2i and I'm cubing it, and I'm taking 3 lots of 1 minus root 2i away, squared, plus 5 lots of 1 minus root 2i, and then I'm taking 3. Now, I really don't think that you're going to be doing anything like that by hand, because just the amount of time that it would take. So use your calculator, and then when you do use your calculator, you find that it's 0. So if it's 0, so we can say the remainder is 0. Which means then that z minus 1 plus root 2i is a factor.
And the conjugate of that would also.
Bingo. And that's what we're going to help us over here with this one. So, as Kobe has said, find the other linear factors. So we know that z minus 1 plus root 2i is a factor. And so the conjugate root theorem then says that z minus 1 minus root 2i is also a factor. So if this is a cubic, how many linear factors is there going to be? You've got a cubic, 3. This is here. We've already got 2, so there's one other that we can do. Alright, so how might we like to find the other? Well, we can use a number of different ways to find the other. But we've already got two of our factors that have got complex numbers in them, and there's no complex number in here as our coefficients. So that would then suggest that the other factor would not have a complex number in it, because if it did, you would have a conjugate and then you would have 4 factors and we only need 3. Does that make sense? So these two, when you multiply them, create real numbers for you. So the other factor, when you multiply it, we can only be working in real numbers, can't we? So what do we want to do? Third factor. Try what? P of
-3.
-3. Why would you try -3? So remember, when you multiply these out, they're going to give you a real number, aren't they? Start with the easy one first. Start with 1. All right, start with the easy stuff first. All right, because here, when you multiply these two things together, you're going to get a real number out of it. All right, so because you're going to get a real number out of those when you multiply them together, you can work out what it is quite easily. The chances are that, yeah, 1 or 3 for here would be one to try. Might as well try the easy one first, though. All right, always try the easy stuff first. 1 cubed minus 3 times 1 squared plus 5 times 1 minus 3. 1 minus 3 plus 5 minus 3 is 0. And so if that's 0, then x minus 1 is a factor. And so our polynomial then would be x minus 1, z minus 1 plus root 2i, z minus 1 minus root 2i. All right, alternatively, you could multiply these out, get your answer, and then divide it into this, but that would probably be more work. All right, anything about that question before I move on to the next?
Is that just supposed to be z minus 1 or x minus 1?
Z. We're working in Z's. Thank you. And so that there should be a Z. Sorry. I've even got Z written in my notes, can't read. All right, another example. All right, a couple more examples. Alright, z squared minus 16 looks like a difference of perfect squares. Alright, so z plus 4, z minus 4, z squared. So it should be z to the 4, I've written the wrong one, sorry. Right, so it's still a difference of perfect squares, but z squared is z to the 4. Alright, now because we have complex numbers available to us, something like this z squared plus 4 in the past, and in methods we wouldn't factorise that, we'd leave it. But because we've got complex numbers, we can factorise that if we change the positive to a negative and put the I squared in there. This other one here has already got the negative, and so then we do difference of perfect squares. With this complex one, it's z plus 2i, z minus 2i, z plus 2, z minus 2. Alright, and again, we've got our complex conjugates there as factors. Alright, so this one here asks us to solve. So what do we need to do to solve? What's our processes that we use? It's the first thing we do. We factorise, thank you. We factorise to get factors, and then we can use the null factor law that equals 0. Alright, so let's have a look. So what are we going to try? P of, start with the easy one. 1. 1 cubed plus 3 times 1 squared plus 7 times 1 plus 5. And I already can see from that, no good. Let's try negative 1 there and see if that makes any difference. Because remember, if it's negative 1, these two terms here are going to negative 1 plus 3 minus 7 plus 5, which is 0. Alright, so what does that mean? Z plus 1 is a factor?
Yep.
Okay. Alright, so let's divide z plus 1 into that stuff. Alright, so I need z squared away. 2z squared. So I'm going to need 2z. So I've got 2z squared plus 2z. I'm going to take that away. So I've got 5z plus 5. And so then it's plus 5 on the end, isn't it? Alright. Okay. So we're asked to solve that. So at the moment, this is what I'm down to. So at the moment, I know z plus 1 is a factor. The other bit is z squared plus 2z plus 5, and that equals 0. Come on.
What's that? I can't see because of the glare. Wasn't she? What are the numbers?
Which one?
It was 2z squared.
Right. I hope they all don't look too much the same. All right. Now what?
Complete the square.
You want to do that? You can do that. You can do that. However, in this question's not asking us to factorise, although you can factorise it, and you'll get there. But I'm just trying to save you some work. Because it says solve, rather than completing the square to factorise, which you could do, what else have you got available to yourself? Quadratic formula. Because we know from this one, we know z plus 1 is equal to 0, and we already found that z equals minus 1. And the other one here is z squared plus 2z plus 5 equals 0. And so, yeah, because we're not asked to factorise it, we've got available quadratic formula, haven't we?
Yeah.
All right, so in this case, z equals negative b, negative 2, plus or minus the square root of b squared, 2 squared minus 4 times 1 times 5, all over 2. Negative 2 plus or minus the square root of 4 minus 20 over 2. Negative 2 plus or minus the square root of negative 16 over 2. So what are we going to do with that negative 16? Yep, so negative 16 becomes 16i squared, yeah? So then when we square root that, plus or minus 4i over 2, I'm going to take out 2 as a common factor. Over 2, the 2's cancel. Negative 2 plus or minus 2i is the other solutions.
Isn't it negative 1?
Yeah.
All right,
it's
I forgot to take the 2. Yep. Good point. Too much for a rush. All right, so because it's asked to solve, you don't need to do the factorising, although you could. You'd have to complete the square like we did in a previous example, and in the end you get that as your answer. So just to illustrate another, when you're solving, you've got the quadratic formula that you can use to help you. All right, anything else? Any questions about that? Anything I went through too quick? Any other mistakes I made? No? All right, we're up to the 4F stuff then.